Thank you, and thanks for having me here. It's actually so beautiful down here, and I'm so lucky to come here to SANSA, hang out for the day, and be here in Hermanus and observing and inhaling your beautiful beach and waves, and along with all the hail today, which is also pretty exciting. I was up in Sutherland earlier in the week, and I think they have snow up there today, and so it's very kind of moderate and warm down here in comparison. So I'm going to talk about astrobiology, life in the universe. When people talk to me and they find out that I'm an astronomer, they ask me one question, which is, hey, do you think that aliens exist? So let's just get it over with. How many people say yes? Do aliens exist? Right on. OK. How many people say no? Fine. OK. That's all good, too. Here's my logic. Let's just go through it. There's 100 billion stars in our galaxy. Our galaxy is the Milky Way. There's 100 billion galaxies in the universe. You multiply those two numbers together, it's 10 to the 22. That's a lot of stars. So statistically, I think at least one other star, probably far more, has a planet with life. So they get that answer. And then the question is like, well, have we ever found any of those? If there's 10 to the 22 stars out there, certainly we've found some life out there. And the simple answer, have we ever found any life, is no. Scientists have been looking for a long time. They've been looking for life on Mars, on other planets, elsewhere in other systems. We've never found any evidence, any undebated evidence anywhere for any sort of life on any comets, any asteroids, any planets, any other galaxies, anything like that. So, no. Those questions out of the way, let's move on. So, maybe the biggest question facing the field of astronomy, field of scientists, field of philosophers in the world today is the question of, are we alone in the universe? I mean, so what scientists are studying is all the laws of physics on Earth. And the broader picture is, do those laws apply elsewhere? Is what was created on Earth similar to what was created in other systems or not? Are we alone in the universe, or is the universe filled with life throughout it that's trying to meet us? We can break that down. Is our solar system unique? Is the Earth unique? Is life on the Earth unique throughout the universe? So let's go back just to give a little historical view here. Go back to the 1500s. Back then, you had this view that, well, of course, the sun is the center of, or the Earth is the center of everything in the everything that we know. The stars go around us, the planets go around us, the sun goes around us, the sun comes up, the sun goes down. Of course, the Earth is at the center. And of course, we knew at the time that we're special. We're the center of the universe. We're the center of everything. Of course, life is the most special thing around. Unfortunately for that view, Copernicus came around and using measurements by the astronomer Tycho Brahe, Copernicus put together this model of the universe with the universe at the time, with the sun at the center and the Earth just as one of several planets here. You've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, the known planets at the time in this sun-centered or heliocentric view. And so we still thought we were pretty special. There was a lot of debate over this with the Catholic Church and so forth. And we thought we were pretty special. I mean, there's still, the sun is still the center of the universe, and there's not other systems out there. But maybe but there are other planets out there. So we're becoming a little bit less special, a little bit less unique. Okay, let's go forward another 100 years. The astronomer Christian Huygens suggested that all these other points of light that we see out there are stars, and those stars are not just like fireflies up there, but are actually basically other suns. This hadn't been proposed before then, that all the stars are the same as our sun. If all those stars are the same as our sun, maybe they have planets going around them as well. And so you put that in the bigger context, and here you have a sketch of our Milky Way galaxy. This is just an artist's rendition because we're in the galaxy and you can't take a photo of it. We're about out here, with it being an undistinguished star out near the edge of it. And there's all these other stars out there that could be similar to ours. So we're becoming less and less special here because we're just one of 100 billion stars in this galaxy. Fast forward again, you can see where this is going. So Edwin Hubble, the American astronomer, saw these spirals of light in the sky and proposed these are galaxies. These galaxies are essentially other Milky Ways. The universe is everything, and these things, like the Milky Way and like these spirals here, are the galaxies. Each of these galaxies has 100 billion stars in it, just like our galaxy, the Milky Way. And so he proposed that was what was going on, and that suddenly we've expanded the size of the universe by 100 billion times because you have 100 billion galaxies, just like what we can see here. And so to be clear, all of the stars that you see, if you go outside at night, you look up, all those stars are in our galaxy. Everything you can see is in our galaxy. The only thing that you can see which is a little bit outside our galaxy, if you look at the big fuzzy clouds, those large and small Magellanic clouds near the Southern Cross, those are essentially other galaxies or nearby other galaxies. And so this view is that we're becoming much less special and much less unique. In the last 2 decades or so, we've started to find planets around other stars as well, extrasolar planets or exoplanets. We see these around a lot of stars. In fact, it turns out that the number of planets out there may exceed the number of stars. So many stars that we've seen have, this is a sketch of some of them, many stars that we've looked at have 3 or 4 or 5 planets going around them. Some of them have 1, some have 0. But if you add those all up, there's probably more planets out there than there are stars. And so we're becoming less and less special through time here. In fact, as it's looking now, we occupy just a tiny, tiny, insignificant corner of the universe. There's really nothing special about where we are. There's nothing special about the composition of our solar system or of our Earth. There's billions of other planets around billions of other stars in our galaxy, and many of them may well be very similar to ours. So is our solar system unique? No. Sorry, is the Earth unique? We haven't found a planet which is exactly like the Earth yet, but it's probably just a matter of time, a matter of building more telescopes to search slightly deeper and deeper. It's easier to find these planets like Jupiter because they're much bigger and easier to find than it is to find something like Earth, it turns out. Is life on Earth unique? We don't know the answer to that. So I'm going to talk a little bit more about what we mean by life and how we can search for life elsewhere. So let's just go through this. If you were to put some biologists and scientists in a room about 20 years ago and ask them, what are the if you want to search for life, where would you look? What are the sorts of environmental characteristics that would define how you would search for life? I mean, you want to search in this temperature range and that kind of thing. So let's put a list of those things together as if we're scientists back then. You want something not to be too hot or not too cold. You can't have, on Earth here, you don't want life to be above boiling. You don't want it to freeze because it's going to die. We'd all die if we froze, right? Okay. You don't want to be too acidic. Like if you're stuck in battery acid, you're going to die. Not too saline. I mean, if you stick yourself out in the, you're going to get desiccated. I mean, that's what the Egyptians did when they dried people out. You don't want to be too high pressure. You can't bury yourself at the core of the Earth because you get squeezed to death. You can't live in a nuclear reactor. I mean, that's why there's those signs to keep people out, because radiation damages cells. You can't have too much ultraviolet light. That's why you put sunscreen on, because that damages cells as well. All life we know is based on reactions of carbon, hydrogen, oxygen, nitrogen, potassium, and everything we know uses liquid water. But with a little bit of, so here's our list. But with a little bit of hindsight, we can actually go through and analyze and look at each of these things on here and see, well, this first one, life requirement has to be below the boiling temperature of water. This is a picture kind of looks abstract, but I'll clue you in a little bit that this is a walkway down here. And this is a park bench down here. These are people walking. This is a picture, and there's another person over there. This is a photo from the air over the Yellowstone National Park in the States. And the reason why this looks all crazy is that there's all sorts of bacteria that are swimming around in this little lake. This is about 100 meters across. And we see all these bacteria, which we call thermophilic bacteria. They live at much higher temperatures than anything that we really know of, or that we know of from our normal everyday existence. With us, if you put something in water that hot, it gets cooked. That's why you take an egg and you put it in boiling water, because it breaks apart the proteins and destroys any possibility for life. But what we found in Yellowstone and other areas is types of life which love this heat. We call these thermophilic, heat-loving bacteria. We see these in Yellowstone. This is also down at the bottom of the ocean. We see these seafloor vents where hot water comes out of the ocean. Temperatures of up to about 120 Celsius. You might think, hey, that's above boiling. How can it get that hot? Keep in mind it's at high pressure. So the boiling temperature is actually quite a bit above 100. So we see these bacteria all over the place. OK, so let's cross off that requirement. Not too cold, because if you're cold, that's going to, if the water freezes, it bursts your cell walls, right? OK, so here's a guy. He's down into Antarctica. He's looking around for life in Antarctica at about -20 Celsius. And in fact, we find life which can reproduce and live and metabolize and all the stuff that we think of as life doing at these low temperatures as well. So let's cross that one off. OK, not too acidic. Fine. Here's some mine runoff. This is actually at a region in Spain called the Rio Tinto. This is a mining region which has been used for thousands of years. So it's very heavily polluted. It looks awful, but what a lot of this is actually bacteria, which is acidophilic. This is a very low pH region, so very high acidity, and pH of around 2. Why does this keep doing this? I'm sorry. Cancel and kill yourself. Sorry, that's not what I meant. That's really rude. OK, hang on just 1 second. Turn Wi-Fi off. OK. That's not what I need. OK. OK, so let's cross off this acidity requirement. Not too saline, not too salty. This is a region in the salt pans in Botswana, where it's very dry now, but the rain is going to come down, and it's going to mess up this area and turn it back into a very dense, very salty lake, essentially. What we find here is bacteria which love this very salty area. It's about 10 times as salty as anything you find in the ocean. So we call this halophilic bacteria. Not too high pressure, OK. Here's some pictures taken down at 10 km below the surface of the ocean. We actually find these creatures. These are about the size of a rugby ball, about yay big, and they just kind of motor along the surface of along the bottom surface of the ocean. These are animals, pretty macroscopic, and they survive and they love these really high pressures. We call them piezophilic, pressure loving. So we can cross off that requirement there. OK, not too much radiation. Fine. We see this is some of my own work where I'm looking at the sorts of radiation environments which can be beneficial to starting life or to making the early chemicals that make life. And what we're finding is that this UV ultraviolet radiation can actually be very beneficial in the earliest stages of forming life. Based on carbon, hydrogen, nitrogen, oxygen, potassium. Let's see. Well, OK, so all life that we know of likes oxygen, right? Or uses oxygen somewhere in there. This is a discovery of some little animals. They're not bacteria. They're actually animals called Spinal Orcas. And they come from the bottom of the ocean in the Mediterranean. These are about 1 millimeter across. And what we find with them is they don't use oxygen at all. You might think, hey, well, they're in the water. How can they not use oxygen? And what happens here is that these things are they're buried very deep in the mud underneath the Mediterranean. And the Mediterranean right there is very cold, and it doesn't circulate at all. So there's essentially no oxygen in the water. The water is still made up of H2O, but these creatures can't break apart that into their atomic compounds. But there's no oxygen in the way that we would use it either. So they survive very well with no oxygen at all. This is a picture of a region in Mono Lake in the southwest United States, where there were some creatures that were recently discovered that was thought used arsenic instead of potassium for their chemical processes. First time that had ever been found. It looks like the evidence is that this was not correct, and they actually do use potassium in the first place. But it sort of opened the door to finding other chemistries to what we normally think of as life. And so we're left with just one requirement here, which is that life uses liquid water on Earth. Turns out it's the only one that's left. All life that we've ever found anywhere uses liquid water. Even this life, which runs at very cold temperatures, has essentially antifreeze to liquefy the water. And so that's our one requirement for life, our one common requirement. And so essentially, the search for life, as we know it, in the solar system, is basically the search for liquid water. Water itself is very common throughout the solar system. We see water almost everywhere, H2O. Water is found in these three different forms, as steam, as liquid water, and as ice. It's more common to find the liquid and frozen forms of water than the gaseous and frozen forms than the liquid form. But water is pretty, the reason why water is pretty common, if you just look at it, this is just a chart that shows the abundance of the different elements versus their elemental number in the periodic table. And so over here you have hydrogen. Hydrogen is very common throughout the universe. And then you have helium. And then you have oxygen over here. And so, 1, 2, 3, the three most common elements throughout the solar system are hydrogen, helium, and oxygen. Hydrogen and oxygen. It doesn't take much of a stretch to imagine that water is really common because it's made out of two of the three most common elements in the whole solar system. This is the solar system, but other galaxies, other stars have pretty similar compositions to what we find here too. So water is pretty common everywhere. So it's not much of a stretch to see why it would be used in life in life on Earth. So if we're looking for water, where should we look? Looking for liquid water. And why liquids? Also because most chemistry happens much faster in liquids. You can imagine that if you have an ice cube in your freezer and so something else that's frozen next to it, they kind of stay inert there. I mean, there's not much action that happens between this and the table below it because they're solids. Like with gases, the densities are often too low, and so you can't have fast reactions happening. But between liquids, they're much more beneficial, much more easy to make chemistry happen in liquids. So, number one place you've probably heard about life and searching for life in the solar system is Mars. This is a nice picture. I'm putting this up there. This is a pretty old picture, actually. It was actually made from you can see where these photographs essentially were stitched together. This is from the Viking mission to Mars in 1976. I'm putting this up just because it's old, because we've known about water on Mars for a long time. What you're seeing here, this is kind of like a Google Maps image. It's a couple kilometers, maybe 10 or 20 kilometers across on the side. And what you're seeing here are drainage channels where there's water that came down on the surface over here and then drained out into big gullies down here with the different rivers merging together. Very much like you'd have on Earth. We see these drainage channels all over Mars. And what we don't see on Mars is water right now. But we do see evidence that Mars used to be very wet. In fact, the total amount of water that was on Earth, or that was on Mars, was the size of several of the oceans and seas put together on Earth. So we had a lot of water there. We don't know where that water went to now. It's one of the big mysteries relating to Mars. We don't know where the water went to, whether it floated off into the atmosphere and was lost to space, or whether it froze out into the surface and became sort of a permafrost, kind of a tundra. There's a mission to Mars which is flying right now, which is on its way there, called MAVEN, which is actually going to explore this possibility. There's some evidence for liquid water on the surface now, like here's a new drainage channel that has shown up and wasn't there, a year ago. But it looks like most of the water is gone on Mars now. And there's also some debated evidence that that we've actually found life on Mars. This is a rock that's about the size of a potato that was discovered in Antarctica in 1984. And there were some scientists at the NASA Johnson Space Center in the mid-90s who took this rock and they broke it apart and they took electron microscope studies of it. And they found a lot of interesting features in it. Among them were things like this thing here. It's colored green just so you can see it. It doesn't actually look that way. But this is very small. It's about a micron across. And what they proposed is this is a fossilized, essentially, the fossilized bacteria from the surface of Mars. This rock, we know from its composition and from some of the gases trapped in it, we know this rock is actually from the surface of Mars. It was on the surface and it was ejected into space and then landed in Antarctica where it was recovered. And so the debate is kind of still open on this, but it's pretty sketchy evidence that hasn't really been confirmed by more follow-up work in the 10 or 15 years since this first came out. But this is the closest we've ever come to actually, maybe discovering any direct evidence for life in the past. Okay, so we've got Mars. We have a lot of spacecraft which are cruising around the surface of Mars or flying around or have been in the past, which are looking either for life or for evidence to support the fact that there might have been life in the past, or to fill in all these holes in our knowledge of Mars's history, and so forth. So this is one called the Curiosity Rover. I'll talk a little bit more about it later, but it's has a bunch of experiments on board it, which are looking for the history of habitability on Mars. Did Mars used to be wet? How wet was it? For how long? That kind of thing. Okay, so there's number one, Mars. Number two best place to look for is this moon of Enceladus, which is the moon of Saturn. Enceladus is really cool. It's a moon which is about the size of our moon, orbiting Saturn. We've known about it for a long time. It's a pretty big moon. And what we found with because there's a spacecraft called Cassini, which is orbiting Saturn. And it was taking some pictures of Enceladus and said, hey, look at this. There's these plumes coming off the side of Enceladus like this. And these plumes come and go. And we can actually take our spacecraft and fly it through these plumes, and essentially it kind of sticks out its tongue and samples the material in those plumes, and it can tell that they're made of water, probably salt water. And so if this water, they're frozen solid by the time that they get to our spacecraft, but in order to be ejected like that, there almost certainly have to be liquid water on the surface of Enceladus. And so we probably have like a subsurface ocean where something is keeping this ocean warm underneath Enceladus, and these plumes are being forced up through the crust of Enceladus and out into space. We don't know exactly why they're keeping warm, but the point is that there's liquid water there right now, which is warm and active. Enceladus otherwise would be a nice cold rock, but something there is keeping it warm, and that means it's very interesting from a standpoint of life. Cassini's flown through these plumes a couple of times, okay, looking for salt, right. And in fact, there's been, just in the last couple of months, there's been some new Cassini results. What this says here, this is a NASA space asset. This detects ocean inside Saturn moon. And this is a press release from April, 2 months ago. And what it says is that Cassini's flown by Enceladus very close, and basically we used the spacecraft as a gravity meter. We flew it past Enceladus and detected how much its orbit was changed by the gravity of Enceladus. And you can actually use this to probe the interior of Enceladus, because Enceladus is made up of a core here, and a crust, and a mantle, and a little bit of an ocean here. And what they found out is that if they didn't put an ocean in there, then they couldn't get the model to match. And the only way they could actually match the gravitational tug on the Cassini spacecraft as it flew through was by putting an ocean into their model. And so this is very strong evidence that in fact we do have this ocean on the south pole of Enceladus with liquid water in it right now. So this is really a pretty exciting discovery. Number 3 place for looking for water in the solar system is on a moon of Jupiter called Europa. And Jupiter also is Europa is also a pretty big moon. It was discovered by the astronomer Galileo in the 1600s. And this picture here is a couple km across, and so it's showing these blocks here. And what you can see is these are like basically icebergs made of ice that are essentially floating on what used to be a liquid layer here, where this is kind of a liquid ocean, and these blocks are icebergs floating above it. The surface is now frozen solid, so we don't actually see any liquids on the surface now. But what we do see is that very recently it used to be all liquid, or it used to be these icebergs floating on the surface. And so probably what's happening is that there's a subsurface ocean here, something like this, with the ice layer above it, and then a core down below, which is keeping this warm. And so I showed you these pictures earlier of these hot smoking vents where there's a hot core at the pumping out hot water from the bottom of our ocean. That's very similar to what's happening here. And so if that could be the source of life on our Earth, it could also be the source of life on some place like Enceladus or Europa. I'm sorry. So right now we don't have a spacecraft which is studying Europa, but in the next decade we expect the European Space Agency to send a mission out to Europa. Something called JUICE, which is the Jupiter and Europa Explorer mission. And this is actually one of its goals is going to be to characterize Europa and see if we might see evidence of life on the surface of it. It's not going to be a lander. It's not going to dig around and look for stuff. It's going to do it from orbit, but it's going to give us the closest view of Europa that we've ever seen. What about outside our solar system? All these things I've talked about are still very close. We've sent spacecraft throughout our solar system to almost to all the planets, with something going out to Pluto right now. And NASA has been doing that for about the last 50 years or so, and we have that down pretty well. On a scale model, if we send a spacecraft out to our solar system, even out to Pluto, it gets to about here, and it takes about 10 or 15 years to get out to the outer edge of the planets in our solar system. On that same scale, to go to the next planetary system over, we'd have to be most of the way over to Cape Town to go to the next stellar system. And so sending spacecraft out to other stars to look for life there is a much, much more difficult game than sending spacecraft to explore our own solar system. So for right now, we're really limited in our direct exploration to look at stuff in our solar system for life. Okay, so some of you are going to say, like, well, hang on, this whole thing, like, you're just looking for liquid water and you're looking for like carbon-based chemistry, like we are so biased, we are so like limited in what we're looking for, what's going on. So in fact we are. And so it's very much a correct accusation to say that we're looking for life that looks like us. So let's look at that. So we're talking about carbon-based life, we're talking about water-based life. What's the deal? Okay, so carbon, first of all, why do we talk about ourselves as being carbon-based? Because most of the chemistry that goes on in our body involves carbon. Respiration, where you have carbon dioxide. Digestion, you have methane produced. Energy, carbohydrates, it's the word carbohydrates, right? Any sugars, anything that you get energy from requires carbon. Anything that you breathe in has gives off carbon. The basic fundamental building blocks of life with amino acids and proteins are all built around carbon. And so that's what we say when we're talking about ourselves as being carbon-based life. Carbon is pretty cool. I mean, it's a pretty neat atom. What's cool about carbon is that you can build so many different other molecules with carbon. There's about 2 million different molecules that chemists have indexed in the lab, and about 1 million of those are built around carbon. And it has to do with just the bonding properties of carbon, that it's very easy to bond with it, and it's very easy to bond with other things. And so there's just a lot of molecules that love to bond with carbon. Carbon is also really easy to break bonds with, and so you can do chemistry easily. You know, you can bond here and then break apart and do some chemistry with another molecule and then recombine and reform, because that's what life is all about. It's about changing. And carbon is very easy to do that with. Carbon, of course, is also very common in the universe. Most common things in the universe by number: hydrogen, helium, oxygen, and carbon. So it's not too much of a stretch to think that any sorts of complex chemistry are based around something which is a very common atom in the universe. If you look at the periodic table here, okay, so what about silicon, right? Because that's something that sometimes people talk about as being maybe you could have a silicon-based life instead. So so here we have our periodic table. You have carbon right here, and basically this column of the periodic table is the column where chemistry happens the easiest. These molecules here, or these atoms here, bond and unbond the most easily with other species, and they form the most other number of compounds. So you have carbon and silicon, germanium, tin, lead, fluorine down here, because all of these things here have 4 bonds. Things over on the right here become pretty inert. These are the noble gases over here. They're very inert. They don't combine with anything. And this is where most of the action is, right here. So you can look at silicon-based life. Oops. Gets out of order there. So you can look at silicon-based life. Turns out silicon doesn't easily combined, doesn't easily uncombine with things. It's pretty easy if you have silicon for it to for you to sort of get stuck in an area where then no more chemistry can happen, and you just end up with basically dust, sand, which is silicon dioxide. It's also possible we don't understand silicon very well, and we're biased in how we're studying it. Water also is pretty special. In addition to being made out of common species like hydrogen and oxygen, it's pretty polar, so you can dissolve a lot of things inside water. Salts and sugars and alcohols and things like that. Lots of things for chemistry. It's very common. It has some properties that might stabilize life, such as if you have a cup of water, it stays liquid water for a long time. It doesn't easily evaporate. It doesn't easily freeze. That can stabilize any forms of life. Ice floats also. If you notice in these pictures I showed you, cutaways of Enceladus and of Europa, you have an ice sheet on top with liquid water down below hand, And that ice on top is protecting all that liquid water from escaping into space. And so that may be one of the benefits to having life based around liquid water. Broad temperature range. Most liquids on Earth don't have nearly as broad a temperature range as water as well. You can certainly come up with a list of other solvents or other liquids that a life would be based around. Here we have water, maybe hydrogen fluoride, ammonia, methane, liquid hydrogen, and so forth. None of these are quite as flexible as water. Hydrogen fluoride is not very common. It's only found in abundance of about 1/1,000,000th as much as water. Ammonia operates at much lower temperatures. Methane also has a very narrow temperature range, and hydrogen is really at among the coldest temperatures here. You don't see liquid hydrogen on really anywhere because it's at such a low temperature. And it's very easy to boil it away. So at high temperatures, chemistry happens much faster at higher temperatures, and so any chemistry of life that would happen in something like hydrogen would happen extremely slowly because it would have to be at very low temperatures. Doesn't mean it couldn't happen, but it does mean that it's very different than the life that we know of here. So from what we can tell, water and carbon are pretty special, but we certainly can't rule out the fact that we are so biased or clueless in our studies to miss other chemistries. So let's assume that you have life on Earth. Where did it come from? And there's kind of two different philosophies of how life started on Earth. And the most direct one, you just build it from scratch. I mean, you start off with atoms. You can build those atoms into molecules. Take those simple molecules, build those into more complex molecules. Take those complex molecules, build them into amino acids, these long chains. From there, you go into DNA, and from there, you get life, right? And some of these steps are pretty easy. My research studies some of this work here in the middle. Some of these steps, like from going from amino acids to DNA, are extremely complex. There's millions and millions of things that have to work out there to actually build life. And it's kind of surprising because it looks like, if you look at the history of Earth, life came out very, very soon after it could have. It didn't take very long for all these steps to happen. So that's model one. Model two is, well, let's not worry about the problem. Let's just say life came from somewhere else. We know that we get a lot of debris from other planets and from other systems in the universe that come to Earth. When you have a comet that crashes into Earth, when you have an asteroid, when you have a shooting star, which is just a little meteor, all these things are debris from elsewhere in the solar system, or even from other solar systems, which are impacting into the Earth. These things happen all the time. We see these impact craters on the surface of the Earth, like the Vredefort impact structure outside of Joburg, where there's something which is many kilometers across, which crashed in, bringing who knows what with it. It could have brought life, or organic molecules, or seeds, or bacteria, or anything with it, if that life was developed on a different planet instead. This idea is called Panspermia. And right now, from what we know about the Earth and from what we know about biology, we have no clue which one of these two models is actually where life came from. It's a huge open question. So I want to mention the Mars Curiosity Rover. This is a large rover which is driving around the surface of Mars right now, looking to explore the history of habitability on Mars. This launched in 2011 from Cape Canaveral, which is the launch site at the Kennedy Space Center in Florida. This is a NASA mission with a couple of contributions from partners in Europe. It's close to 1,000 kilograms, and it has a whole suite of instruments on it, which are doing various studies, taking photographs, taking spectra, picking up rock samples, doing lab analysis on them, and so forth to study the chemistry and the history of chemistry on Mars. So I have a short little movie that I just want to run, showing you about how hard it is to get to Mars and the amazing work that, some of the engineers have done on getting this thing there.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering, thought, but it still looks crazy. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away. So when we first get word that we are at the top of the atmosphere, the vehicle has been alive, dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from here. If any one thing doesn't work just right, it's game over.
Slam into the atmosphere, it develops so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently to the atmosphere, but also we are guiding like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
It opens up that fact.
Oh, man. Okay. Hang on. I'm sorry.
No choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, we're going to do something. We're just going to smack right back into the parachute. So the first thing we do is make this really radical diversion. Fly off to the sun.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land, and straight down to the bottom of the crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend compulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skycrane.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its with us on the surface.
As the rover touches down and is now on the ground, in the same state, it's in a collision course with the rover. You must cut the bridle immediately and fly to the same stage to a safe distance from the rover.
I just get shivers every time I see that movie. It's so fantastic to think of being able to fly these missions and against all odds have them work. So here's what the Mars Curiosity Rover is doing. It's been there for about 599 Martian days. Martian days are a little bit longer, about 15 minutes longer than a terrestrial day. So you count them in sols, not days, because that would be confusing. Its job is just to drive on the surface of Mars and inspect things that are interesting. It's driven by a group of engineers at the Jet Propulsion Lab at NASA's center in California. Last month, it finally arrived at a region called the Kimberley, which is a whole bunch of mess of diverse rocks, which is going to be inspected and studied for what it can say about Mars's history. There's some minor issues with some of the instruments, but nothing which has threatened the mission at all. It's going extremely well and has been doing a lot of great science. There's a press release that came out about a year ago, studying the history of water on Mars, and what they found here is that several billion years ago, Mars may have well have been a pleasant place for microbes to live with plenty of water, as well as minerals, perhaps for food. However, we have not found signs that actual microbes did live there. What we found is a habitable environment that is so benign and supportive of life that you could drink the water if you were there, and so forth. So this actually is not that much of a surprise. I mean, we've seen these pictures where there's been water outflows for many decades. And the thing they haven't found yet is any evidence for life itself. Different press release about a year later looks at the history of methane on Mars. Methane is interesting because it's on Earth. Methane is produced in just two different ways. One is in digestion, and from rotting, anything that's rotting on the surface, or anthills or cows or anything like that, produce methane. And that goes into the atmosphere. The other place that methane is produced is in volcanoes, because it's dredged up from lower down, and it's given off in great quantities by volcanoes. And so there was some early evidence that from studies from Earth that methane was seen on Mars, and that was really exciting because, as far as we can tell, there's no active volcanoes on Mars. And so any methane that we do see there would either say there's active volcanoes or there's life on Mars, something rotting. And so that would be really interesting. Unfortunately, for the prospect of life, data from the Mars Curiosity Rover has revealed the Martian environment lacks methane. This is a surprise to researchers because previous data reported by the US and other scientists indicated positive detections. And basically, there's a little methane sensor here, which has been sniffing the atmosphere for the past year, and at very high resolutions, much more sensitively than you can study it through telescopes from the Earth, and found that the limit of methane on Mars is 1.3 parts per billion. It's about 1/6 as much as these earlier measurements put a limit on. And so, from that standpoint, certainly there's no direct evidence for active life on Mars right now. So if you look at the history of Mars exploration, we can put this in a historical sense. This is, I don't expect you to read this, but what this is just a dump from the Wikipedia page on the history of Mars missions. And the point here is that it's in a very small font because there's been a lot of Mars missions. The important thing to look at here is the color code, where red means it failed and green means it worked. Time goes down this way, so this starts back in 1960s. And we've sent 50 missions to Mars, and less than half of those have actually been successful. Most of them have either crashed into the surface or blown up on launch or been turned off accidentally or had a software bug or things like that. And so Mars is a pretty hard place to go to. But we still have sent 22 successful missions to Mars. And these 22 successful missions tell us one thing, which is that none of them have found any life there. I mean, 22 times is a lot of times to go to the same planet and keep looking for life and history of anything there, and keep coming up with the same answer. So really, there's all these other planets out there, and it's time to go to some of them instead. And why do we keep finding the same result on Mars, that Mars is dry and dead and there's no life there? Let's look at the history of Mars. Well, let's look at the history of Earth first. So this is just a timeline going from the past at Earth's formation 4.5 billion years ago. After the Earth was formed, it was still subjected to what's called the late heavy bombardment, which is where you still had a lot of asteroids and meteors and so forth coming in and building up the final stages of the Earth. And as soon as we got past that state, about 3.8 billion years ago, there's evidence that the Earth was wet, which I've colored in as blue here. And you had some early bacteria that came out on Earth almost as soon as it could, about 3.8 billion years ago. You had stromatolites and blue-green algae, some of which are found in out near KZN as the earliest evidence for life on Earth. Within a billion years after that, what these bacteria do is they take in carbon dioxide and they crank out oxygen. And so it took them about a billion years to crank up the oxygen enough so that we actually see the evidence for all this oxygen in the Earth's atmosphere. As far as they're concerned, oxygen is a huge toxic poison. And so because that was a massive restructuring of the Earth's atmosphere to crank all this oxygen into it. But what that did enable is other types of chemistry to happen, which were very different chemistries than the chemistry that blue-green algae uses. So multicellular organisms use oxygen. Animals use oxygen. So we build up invertebrates and land plants and finally people in this timeline. So let's see where Mars compares there. So Mars was formed at the same time as the Earth, 4.5 billion years ago. Late heavy bombardment, the same. Had some water on the surface at the same. But then, about 3.5 billion years ago, the water all disappeared. And instead of being a wet, warm environment for life to evolve in, it's been dry and dead. And it's been dry and dead. And it keeps looking dry and dead. And we keep sending the spacecraft there, and the spacecraft keeps saying, oh, I'm sorry, it's dry and dead. It's dry and dead. There's nothing here, nothing here. And it's basically just the history of how much water has been there, that it's not much of a surprise that we don't see anything there. And perhaps there might be evidence, fossilized evidence for very early life on Mars that's still there. But this evidence is so hard to find on Earth, even though there's been billions of people on Earth walking around picking up rocks for the past millennia. And it's only recently that we found these early evidences for life on Earth. And so it's not much of a surprise that we don't see that on Mars at all. Just had this brief window to host life, and either it succeeded, made life then, or it didn't, but any record of it is almost certainly lost entirely. You can also look at the history of Enceladus, or Europa. And what do we see there? I mean, Enceladus was formed at the same time and had that late heavy bombardment here at the same time. But now it's been wet and warm for the past 4 billion years. So, hey, maybe Enceladus would be a great place to look for life. Or Europa, same thing. So let's send some spacecraft out to Enceladus and Europa. Been wet and warm for all this time. Who knows what we find underneath these oceans in other worlds, but almost certainly they're going to be something interesting up there because of the very different history of what's been happening there. So just a couple of closing thoughts here. We're pretty unique, but we're not that unique. It's certainly true that if you look at all the planets in our solar system, each of them has its own path through history, but there's some shared some shared similarities, and we're still trying to answer the question of how similar are all the planets in our solar system to the planets and the processes and the chemistry in other solar systems. We've learned a great deal about sort of how unique our Earth is, but we haven't learned anything about how unique life is. We don't have another sample of it to really put what we have here in a context yet. Our solar system is kind of what we're looking at now for where we study life and where we study where we came from, because it's another ballgame to start looking for life in other planetary systems. So that's what I have, and thank you much.